of our first topic, wherein we are going to discuss about the introduction to CNN. In our previous topic, we have seen how CNN has evolved. Now we are going to see a little bit more on what exactly is convolution, what are the components of CNN, how does an overall glance of CNN looks like. So what we studied in our last topic was how CNN drastically reduced the number of the parameters that you were going to actually work with, correct? So now we are going to see now about convolution operation. So under the priori of a local correlation, what are we going to produce? We are going to produce a simple layer which we call it as a local connection layer. Okay, now for all the pixels in the window of k by k, which is your receptive field, which I already defined in my last topic. So for all the pixels in the window of k by k, features, what are all features are present inside that image of k by k. So that feature information particularly in that particular window is extracted when you multiply the accumulating weights which are present and you multiply that to all the pixels of this receptive window. Okay, and then each output node extracts the feature which is corresponding to the receptive field area. Don't worry on this, I'll show you one diagram so that you will understand it. Just for now, you understand what is happening here is you have this receptive field, right? So suppose this, out of this big image you have this receptive field. Okay, now for this receptive field you always have weights associated, correct? So because you are doing weight sharing, so every receptive field will use the same set of weights. So the pixel values of this receptive field, it's getting multiplied and cumulated sum is taken at the end to extract the features of this particular specified area of receptive field. Now what exactly we call these particular weights when it gets projected onto this particular image? We call it as a kernel. What is a kernel? We will see. Also known as a filter. Okay, you might have come across this term, filter mode. Okay, so now after you perform this particular operation, what you require as an output is obtained, which is nothing but all the features relevant to this particular space is getting extracted. So now this particular operation is actually a standard operation in mathematical processing, in signal processing, which we call it as a discrete convolution operation, wherein what we are doing is we are keeping one of the function. Now if I take this particular image as one function, I keep it as constant and I am shifting this particular kernel on it. First it will be here, then it will be here, and it gets shifted. So what you are doing, whenever you are putting it, this shifted part of the kernel, you are actually multiplying the pixels of your image with that of the weights present in your weight kernel. And then finally, after multiplication, cumulative sum you are obtaining, so that you extract the feature in this area. Then you slide and you take another part. Then you slide and you take another part. And then overall you add it. So that's how we got it. We call it, this particular operation, as convolution. More on convolution we will see in our next subsequent slides so that you will understand it more better. Now, what exactly is a convolutional neural network, or a convnet, or a CNN? In deep learning, it is a class of deep neural network which is commonly applied to analyze visual imagery. So whenever you are working with image data set, the images as your inputs, then definitely you are going to design a CNN for it if you want to analyze it. There are four major components of CNN. The first is we are going to work with convolution part. Second is adding nonlinearity to your model. Third is subsampling your model, wherein you call it as pooling. And finally, what we do is an MLP, or a fully connected layer, which is suitable for your classification if at all you are doing that application. Now, these are the four major components of CNN. Now, before I actually dive into CNN, I first want you to understand the basic terminology. So, I just now explained you what exactly is a filter or a kernel. So, it is also known as a feature detector because it is helpful for you to detect all the features inside an image. So, this is a very big image. For an example, you take a value of k, it is a small value, 1 by 1 or 2 by 2 or 3 by 3 or maximum 5 by 5. We prefer to take its small value, and then what you do, you put this on or project it onto your image, the bigger image. So suppose here I have taken 1 2 3 4 5 1 2 3 4, yeah, so I have here taken 5 by 5 kernel. So this is my 5 by 5 filter which I am projecting it on my bigger image, higher resolution image. Suppose the image is say 210 by 210, then I am just projecting a 5 by 5 kernel on it, kernel or filter or a feature detector, whatever you do. So it extracts the features over this particular area and give me the value from here. So single value I am obtaining. As soon as it gets slide, then it gets slides. Okay, now what to do? See, suppose you have a image. Okay, suppose I have an image here. I am taking a 7 by 7 image for an example. 1 2 3 4 5 6 7, yeah, 3 4 5 6 7. Okay, so I have this image and I have taken here 3 by 3 ka kernel I have fit on it. So I'll try to take another color. Suppose, yeah, okay, so I am taking here a 3 by 3 kernel and I am going to fit on it, correct? So from here what I am going to do, I am going to multiply this kernel ka 3 by 3 with my previous image that receptive field 3 by 3. This is also 3 by 3, this is also 3 by 3. So image has got its data, some pixel value, whatever. You all know na, that color is over there is defined by the amount of the pixel value that is present there. And I have my filter value over there. So when I have this kernel imposed onto this, I get all these pixels multiplied with each other, and what I get is a single value. So entire feature is getting extracted from this. Now this is only this part of the feature. Now what I require to go to the next. So it's my wish. I can actually go with the next 3 pixels, or if it is a more bigger image, then I can leave some of the pixels which I think they are not relevant, and then I can jump on to the next 3. So what I am doing here, whenever you want to produce more lesser amount of volumes as an output, then you skip some of the pixels and then take the next receptive field. So what we call this as a stride. Okay, so you have to now be very careful with these terminologies that we are using over here. So let me be clear with this. So filter or a kernel or a feature detector is a very small matrix that we use for feature detection, and convolved feature or activation map is what you get after the output. When you multiply your image and the kernel and then multiplying and adding what single value that you get, like that you slide your kernel till you get all the image covered, and then you get a very less amount of pixels as output. That is your activation map, or we call it as convolved feature. The other name is also feature map. So what exactly it is? It is nothing but the output volume which is formed by, whenever you keep on sliding this filter over the entire image and try to compute the dot products and the cumulative sum. So that's your activation map, feature map, or convolution map. All three means the same, right? Next is, what is this receptive field? So I told you, right? It is a local region of your image. Image is nothing but your input data. So it is, you have image, over that you put a filter, you convolve it, and you get an output. I hope the process is clear. So this part of the image where you want to impose this kernel or a filter, that is called as a receptive field. It is a local region of input volume which should be of the same size as that of the filter. And suppose it is not mandatory also to use only a single filter. You can even use multiple filters. So how many number of filters you are using at a time determines the depth. So depth is the number of filters. And then, as I told you, you can skip some of the pixels and keep on sliding your filter. So that is called as a stride. How many pixels you are skipping while you slide your filter. So stride has an objective of producing smaller output volumes spatially. So that was about basic terminology, what we will be using. I hope you are clear enough with it. Now, once you are done with the basic terminology, let exactly see now what exactly are you doing in that sliding and calculating that output. So what exactly are we doing? we are doing a convolution operation. So what exactly is convolution? Here I would like to say. So convolution is actually a mathematical operation which has got inputs as two functions. It is going to create a result or an output function for you that will express how the shape of one of the how the shape of one is modified by other. Basically, if I want to talk in a layman language, then using two particular input, it gives me another output which is completely different from these two. But then here, if I talk on images, it will take image input, it will take filter input, and you're convolving to get a feature extraction as your output. I hope I made yourself clear. In very precise way, I explained you convolution here. So basically what convoluting and extracting features does, it preserves the spatial relationship between pixels by learning image features using small squares of input data. It can also detect small meaningful features of an image like edges, patterns, etc. Okay. So now you can ask me, why exactly do you want to go for convolution? My answer is straight away. There are n number of images which are being fed to any artificial neural network model, like here it is a CNN. N number of images. Each image is a very high resolution image, let's say 1024 by 1024. Now imagine the amount of the data that goes into detecting what is the feature or information in the spatially connected pixels. So to understand these spatially connected pixels and getting information out of it, and also decreasing the size of the output, so that processing of further such number of images is easier, we have to go for convolution. So you can see very clearly, this is your image. An image here is, for ease of access, we are taking 5 by 5. We have assumed k as 3. So k, if I take 3, then only 3 by 3 of this particular image, which we call it as receptive field, will be chosen. This and your kernel size should be same. So k is 3, so kernel is also, or filter, the other name is that will also be 3 by 3. User will define what type of filter it is. We will see what are the different types of filters. So this filter or kernel will be imposed over this particular image, and it is going to extract. So how it is going to extract? Pixel by pixel, 1 into 1, 1, 0 into 0, 0, 0 into 1, 0, like that, 1 into 0, 0, 1 into 1, 1, 0 into 0, 0, dot products, okay, 1 into 1, 1, 1 into 0, 0, 1 into 1, 1. Once you have got that, cumulative of it, that is 4. So this entire 3 by 3 size of a pixel is just replaced as a 1 pixel with a value of 4, without harming the information that is present inside this image. So you can see 9 pixels are now replaced by 1. So that is done layer by layer, and this is suppose the first layer of convolution. Based on how much is the size of image and how much you want to shrink that size, you will increase the number of layers of convolution. So it is user dependent, model designer dependent, how many layers you want, until what size you want your data to be. So this is one way of doing convolution I just explained. So now it's very simple. You can try by yourself for certain examples and get the value. So next what you will do, you will put this and you will slide over here. So you will get 1, 1 into 1, 1, and then 1 into 0, 0, okay, and then 0 into 1, you will get 0, and then 1 into 0, you will get 0, 1 into 1, you get a 1, 1 into 0, you get a 0, next is again a 0, next is again a 0, next is again a 1 and a 1, you get a 1. So final answer is 3. So that's how this pixel value is here 3. This pixel value was 4. So like that you keep on sliding and keep on calculating and keep on replacing and get the feature map. So the output obtained here is called an activation map or a feature map. I hope you are clear. So image is given to us as an input. We as a designer will decide the receptive field, which is k, and kernel or filter size will also be k by k, and kernel values, what type of filter goes, is decided by us, and how many pixels to be used, what stride to give, is decided by us, and finally mathematical calculations is all done by Keras and it gives you the value. You need not do it all mathematically. This is just for your understanding. Working with Keras is very, very simple while you design CNN. That also we will see. But understanding what goes inside it, it is important. So now, what are the common kernels? I'll be quickly briefing you on this. So the very first and very important one is an identity kernel. So identity kernel, exactly, it is used when there is no feature extraction because it is having no effect onto the input, and it gives you the same output as an input. It is often used in early layers of CNN whenever you want to maintain spatial dimensions of the input. Whenever you don't want to curve that input down, you will use the identity kernel. Now, next type of kernel, as I quickly go, sorry, next type of kernel is vertical edge detection. So you can note down these values: vertical edge detection and horizontal edge detection. I have chosen here 3x3 kernel. Based on that only I am giving you the value. Application is they are used to detect any vertical edges or horizontal edges in an image. They will highlight the changes in the intensity along the specified direction. Next is blurring kernels. Two categories are there: box blur and Gaussian blur. Box blur dimensions are all one, and blur kernel is used for smoothing and blurring out an image. It will help you to reduce noise, and specifically it is used in applications of denoising the image. There's another one, Gaussian blur. So the value is 1 to 1 to 4 to 1 to 1, and it provides us more smoother blur than the box blur actually, and again it is useful in image smoothing. Okay. Next, sharpening kernel is used when it enhances your fine details inside an image, and also it enhances certain edges. It gives you to make all the features more sharpened and prominent. So these are the values. Emboss kernel, these are the values for sharpening kernel. These are the values for emboss kernel. Emboss kernel is used when you want to create any 3D effect by changing the intensity and directional lighting inside a particular image. Sobel kernel mein you have vertical kernel values these and horizontal kernel values as these. They are actually again used for edge detections in images. They will highlight the changes in intensities both along both vertical and horizontal direction. So you all use these Instagrams and your phones with all those filters that is coming. So what you do exactly? You select a suitable values of pixels inside those things, and they are imposed onto your image, and with that it gives you that blurring effect, that black and white effect, that contrast effect, that embossed effect, you know. So that's why they are called as filters. We in our normal language we call it, I have applied an Instagram filter and it has changed my image. So what exactly are you doing over there? You are exactly doing a CNN operation there, wherein you are imposing that kernel or a filter onto your input image and producing something else as an output. Okay, I hope it makes clear. Now, coming to the next topic of drawbacks of ANN, why you cannot use artificial neural networks for an image data, because as I already told you, there is a high dimensionality of the image data. Also, you cannot understand spatial pattern when you are using an ANN. Computational complexity is very high, and because the number of layers are less, there is more chances of overfitting, and you cannot even go for weight sharing in an ANN. So addressing all of these drawbacks of standard ANN, we have come to a new type of neural network, which is convolutional neural network, and it is used whenever you are processing any visual data or images. So this is a glance at CNN that you can see. So you can see here in this particular thing, you are having a particular image which is broken into pixels. Each pixel is given to the first layer where the pixel value is detected. In the next layer, see, I told you, no, you will use suitable layer of convolutions unless and until the required features are being extracted. Until you identify the features, you will use suitable layers of convolution. So first pixel values will be detected, edges will be identified, you will combine your edges, and lastly, suppose you have identified your features. Once you have done that, then it behaves like a normal MLP or an ANN, and then you will go for a classification or whatever application that you are doing it. So this is just a glance that I am telling. More in detail we will see. Okay, so now this was a glance at CNN model. Now, how do we learn through CNN is, it depends. You will use a combination of convolutional layer and fully connected layers. There are other layers also in between. We will see one by one in detail. But a brief overview, if I want to say, then it's a combination of convolution layers and a fully connected layer. So first, a fully connected layer is actually prefixed with a convolution layer. Whenever an image data is given, first low level features are extracted, then mid level features are extracted, and then high level features are extracted. You can see pixels are identified, edges are identified, lines are identified, and then higher level depth and all, more edges, more in depth features are identified, and then it is given to your normal fully connected or dense layer, wherein you classify it and give you your output as required. So that's how is learning through CNN. And how do we model it, what are the other things, other layers in depth, what are all their functionalities, we are going to see it in our next upcoming topics.